The Pantheon has stood for almost 2,000 years without steel reinforcement. Modern concrete often crumbles in mere decades. This is the mystery of Roman concrete, a lost material science that defies our understanding of progress. By the end, you will understand the secret chemical reaction that makes ancient harbors stronger today than when they were built. We will uncover how seawater became a construction tool and why our industrial recipe abandoned a self-healing blueprint. What does our most fragile infrastructure reveal about the choices we value? Off the coast of modern Israel, the Mediterranean Sea still crashes against a 2,000-year-old barrier. The harbor at Caesarea, built by Herod the Great with Roman engineering, endures where modern equivalents have been rebuilt countless times. Its submerged concrete breakwaters have faced relentless saltwater, wave action, and storms for centuries, yet they stand firm, even gaining strength from the very element that destroys our own constructions. This is not a monument sheltered in a museum. It is a working piece of ancient infrastructure silently outperforming the present. We see a similar defiance in the soaring dome of the Pantheon in Rome. Its unreinforced concrete spans still the largest of its kind in the world. These structures present us with a profound and humbling paradox. Our modern concrete is a product of meticulous laboratory science, with controlled ingredient ratios and industrial precision. We design it for specific compressive strength, we reinforce it with steel, and yet we accept a lifespan measured in decades for our most critical bridges and seawalls. Roman concrete, by contrast, was mixed with local materials, often by hand, using formulas that varied from site to site. It contained no steel rebar. And it was not designed for our accelerated timelines, it was built for eternity. The evidence is literally set in stone, a global collection of silent witnesses that mock our assumptions about progress. Their longevity whispers a question that has puzzled engineers for generations. What secret did the Romans bake into their recipe that we somehow forgot? The clues are not in grand blueprints, but in the microscopic world within the concrete itself, a hidden landscape where chemistry and time have forged an unbreakable alliance. The Romans did not have microscopes, but they possessed a different kind of genius, an empirical eye for materials that nature had already perfected. Their foundational secret was not invented in a workshop. It was scooped from the ground near the Bay of Naples from a town called Pozzolana. Here, the earth provided a fine, gritty sand unlike any other, a volcanic ash born from eruptions like that of Mount Vesuvius. To the untrained eye, it was just dust. But to a Roman builder, this pozzolana was the soul of their concrete. Its magic was not in its strength as a filler, but in its profound chemical reactivity. When mixed with slaked lime and water, this ash did not sit idly by. It began a silent, slow-burning reaction with the lime, a process we now call a pozzolanic reaction. Over years and decades, this reaction creates a dense web of stable, interlocking crystals, a matrix that grows tougher with time. This was the Romans' masterstroke. They were not just making a rock, they were engineering a chemical process that would continue long after the scaffolding came down. Modern concrete, for all its precision, often relies on Portland cement, which forms its primary bonds quickly and then is largely inert. Its aggregates, the sand and gravel, are chosen to be chemically silent. The Roman approach was the opposite. They deliberately chose an aggregate that was alive, one that would partner with the lime in a lasting chemical conversation. The question then becomes, how did they stumble upon this specific, reactive ash from this specific region? The answer lies not in a single eureka moment, but in a culture of practical experimentation and keen observation, a tradition of building that turned a local geological accident into a global empire's backbone. That chaotic construction site holds our second clue, a process that seemed like reckless waste to modern eyes. Picture workers pouring not the safe, pre-slaked lime we use today, but raw, caustic quicklime directly into the mix. This was no gentle blending. When quicklime meets water, it does not simply dissolve, it fights. The reaction is immediate and violent, releasing a surge of intense heat and steam, a miniature volcanic event in the mixing pit. For centuries, engineers examining Roman concrete samples saw this as a primitive mistake. They found tiny, white fragments trapped within the hardened matrix, which they called lime clasts. These were dismissed as evidence of sloppy, uneven mixing, the hallmarks of an ancient recipe that had not yet been perfected. Our modern process is cold and controlled, aiming for a perfectly homogeneous, predictable paste. The Roman method, by contrast, was hot, fast, and seemingly haphazard. But what if those presumed flaws were actually features? What if that intense, localized heat was not a bug in the system, but a crucial part of the program? New research is turning this assumption on its head, suggesting the hot mix was a deliberate act of material alchemy. The searing temperatures may have fundamentally altered the chemistry of the pozzolanic ash, creating a more reactive starting point. More importantly, those tiny, unreacted lime clasts, once scorned as imperfections, are now being recast as something extraordinary, a built-in repair kit. They sit dormant within the concrete like microscopic capsules of potential, waiting for their moment, and their moment comes precisely when the structure is under threat. To see how, we have to leave the bustling construction site behind and enter a world invisible to the naked eye, where the true battle for longevity is fought atom by atom. Inside a modern laboratory, a sliver of 2,000-year-old harbor concrete rests under a powerful electron microscope. The scientist peers into a world the Roman engineers could never see, yet one they masterfully engineered. They do not find a dead, uniform slab. Instead, the screen reveals a vibrant, intricate landscape, a crystalline garden that is still actively growing. This is the heart of the mystery captured in mineral form. The concrete is alive with two key minerals, tobermorite and philipsite. These are not simple components of the original mix. They are rare, plate-like crystals that form only over immense stretches of time as seawater slowly filters through the concrete's pores. Each tiny plate interlocks with its neighbors, creating a dense, reinforcing armor that actually blocks microscopic cracks from spreading. It is a self-organizing repair system built by time and chemistry. Modern Portland cement, when exposed to saltwater, often forms a weak and soluble compound called ettringite, which can expand and crumble from within. The Roman recipe, however, uses the seawater as a catalyst. The salt and minerals in the water continuously react with the lime and volcanic ash, slowly cultivating this internal crystal fortress. This process is a stunning form of geomimicry, where the built environment learns from and collaborates with the natural one. The Romans, perhaps without fully understanding the atomic scale, created a material that did not resist the sea, but invited it in as a partner. The harbor wall was not a static barrier, it was a living interface designed to evolve and strengthen through its very exposure. This turns our entire understanding of durability on its head. We spend immense energy trying to seal our structures away from the elements, to make them impervious. The Roman model suggests a different path, one of integration. What if the greatest strength comes not from defiance but from a kind of chemical conversation? For modern concrete, seawater is a death sentence. It infiltrates microscopic cracks, corrodes the steel reinforcement within, and causes the surface to crack and flake away in a process called spalling. We fight this decay with expensive sealants and constant repairs, treating the sea as an enemy to be kept out at all costs. The Roman formula embraced a radically different philosophy. In their harbor concrete, seawater was not a foe, but the essential ingredient for long-term strength. It is the key that unlocks the material's self-healing potential. Here is how this counterintuitive process works. As the concrete cures, a highly alkaline fluid, rich with dissolved lime, remains trapped in its network of tiny pores. Over centuries, this fluid slowly leaches out toward the surface. When it meets infiltrating seawater, a remarkable chemical exchange occurs. The magnesium and sulfate ions abundant in seawater react with the lime and the aluminous compounds from the volcanic ash. This reaction precipitates new minerals, primarily more of those plate-like crystals of philipsite and other aluminous compounds, directly inside the cracks and pores. Think of it not as corrosion, but as a continuous, slow-motion repair job. Every microscopic fissure that forms becomes a site for new mineral growth, effectively sealing itself from the inside out. It is akin to a broken bone healing, where the fracture site actually becomes denser and stronger over time. This is the transformative relationship we lost, a material designed not to resist its environment, but to collaborate with it. The seawater does not attack the Roman concrete, it feeds it. This process raises a crucial question, however. What supplies the lime for this endless repair cycle, century after century? The concrete's original lime would eventually be depleted. The secret reservoir, the source of this lasting chemical resilience, appears to be those very lime clasts, the white fragments once mistaken for mixing errors. They are not flaws, they are the strategic reserve. Those scorned white fragments are the missing piece of the puzzle. For decades, they were the textbook example of Roman imperfection, evidence of a recipe not yet refined. Then, in 2023, a team of researchers led by scientists at the Massachusetts Institute of Technology and Harvard University published a finding that turned this assumption to dust. Using advanced high-resolution imaging techniques, they peered into the nanostructure of the lime clasts themselves. What they discovered was not a random lump, but a meticulously engineered feature. The clasts are not made of the stable, crystalline lime you would expect from a slow, careful mix. Instead, they are composed of a highly porous, ultra-reactive form of calcium oxide with an enormous surface area. This was no accident. The Romans' hot mixing method, that violent, steamy process, deliberately created these nanoscale reservoirs. Think of each tiny white speck not as a flaw, but as a sealed capsule, a microscopic first aid kit embedded directly into the concrete's matrix. The genius of the system lies in its trigger. Under normal conditions, these clasts sit dormant, sealed away by the surrounding crystalline armor. But when the concrete is stressed, when the tiniest hairline crack begins to propagate, it eventually intersects one of these capsules. Water, whether from rain or seawater, seeps into the newly opened fissure. Upon contact, the ultra-reactive lime within the clast dissolves and then rapidly recrystallizes, not as loose powder, but as a strong, interlocking network of calcium carbonate. In essence, the crack itself becomes the mixing bowl for a new batch of cement. The breach is not just patched, it is chemically welded shut from the inside. This is passive, bulk-scale nanotechnology, a self-healing mechanism engineered 2 millennia before the term was ever coined. The Roman design philosophy was not about creating a perfectly inert, uniform slab. It was about building a reactive ecosystem, a material with a kind of immune system. They embraced controlled chaos, seeding their concrete with these latent repair agents, trusting that time and chemistry would activate them when needed. This revelation makes the longevity of Roman structures not just impressive, but logically elegant. It also casts our own industrial choices in a stark new light. How could such a profound and effective concept simply vanish from our collective knowledge? The answer is not a single moment of forgetting, but a slow turning toward a different set of priorities, a path paved with the demands of speed and scale. The collapse of the Roman Empire did more than topple statues and redraw borders. It shattered a vast and intricate knowledge network. The specific volcanic ash from Pozzolana was no longer shipped across the Mediterranean on imperial supply lines. The guilds of master builders who passed down the tactile secrets of the hot mix through generations of apprenticeship slowly dispersed. Their empirical mastery, a deep understanding of materials born from hands-on trial and observation, began to fade into local folklore. Concrete did not vanish overnight, but its recipe devolved. Builders used whatever local materials they had, often without the reactive ash, and the profound chemical understanding that turned a mix into a living material was gradually lost. For centuries, construction relied on older Roman ruins not as inspiration, but as literal quarries, cannibalizing the ancient stone because the knowledge to recreate it had slipped away. This was not a sudden amnesia, but a slow cultural sunset. Then the world changed pace. The Industrial Revolution demanded a new kind of building material, one that matched the rhythm of steam engines and factory clocks. In 1824, in England, a bricklayer named Joseph Aspdin patented a new substance he called Portland cement, named for its resemblance to the high-quality stone quarried on the Isle of Portland. His invention was a product of its time, created by burning limestone and clay in a kiln and grinding the result into a fine powder. This powder, when mixed with water, set quickly and achieved high strength in a matter of days. It was predictable. It could be manufactured on an enormous scale in factories far from any specific volcanic deposit, and it was perfectly suited for the rapidly expanding railroads, factories, and cities of the modern age. Portland cement was a triumph of standardization over specificity, of speed over slow curing, of uniformity over localized variation. But this revolutionary convenience came with a hidden chemical cost. The high-temperature kilns used to produce Portland cement create a different suite of compounds, primarily silicates that react rapidly with water to form a rigid, dense paste. This paste gains strength quickly, but its chemical activity is largely front-loaded. Once set, it is relatively inert and brittle. More critically, its chemistry is vulnerable. The steel reinforcement we embed within it for tensile strength is protected by the highly alkaline environment of the fresh cement. But when cracks inevitably form, water and chloride ions from seawater or road salt seep in. This leads to corrosion, a destructive expansion that spells the end for most modern structures. The Roman formula, by deliberate contrast, was never meant to be inert. Its chemistry was designed to be ongoing, using slow pozzolanic reactions and latent lime clasts to adapt and heal. The industrial choice prioritized the economics of rapid construction and the certainty of early strength tests over the long-term environmental synergy the Romans had mastered. We traded a conversation with nature for a declaration of dominance over it. This fundamental shift in philosophy is embedded in the microscopic structure of the materials themselves. One is a closed, finished system, the other is an open, reactive one. Our modern infrastructure is built on the former, while the ancient ruins that outlast it whisper of the latter. This realization forces a difficult question. If we now understand the ancient blueprint for resilience, can we actually relearn it and build it back into our world? The difference between these two materials is not just about ingredients, it is a clash of chemical philosophies. Modern Portland cement is engineered around a compound called tricalcium silicate. When mixed with water, it undergoes a rapid hydration, forming a rigid glue known as calcium silicate hydrate gel and a byproduct called portlandite. This portlandite, or calcium hydroxide, is the weak link. It is relatively soluble, meaning over time, water can slowly dissolve and wash it away, leaving behind microscopic voids that weaken the structure from within. It is a chemistry designed for a fast set and high early strength, but one that is ultimately static and vulnerable to erosion. the Roman recipe operates on an entirely different principle. Its mixture of lime and volcanic pozzolana creates not a single quick reaction, but a slow, complex cascade. It forms a family of gels known as calcium aluminum silicate hydrates. These are far more stable and, critically, they are chemically hungry. They are designed to interact with the environment, to pull in elements from seawater or even the air itself to form new, strengthening minerals. Think of it this way: Portland cement is like a ceramic plate fired in a kiln to a finished, brittle state. If it chips, it stays chipped. Roman concrete is more like a living coral reef, constantly pulling minerals from the water to grow and repair itself. It is less a finished product and more an initiated process, a low-energy chemical conversation set to run for centuries. This is the core of the lost wisdom. We chose a material science of closure and control, prioritizing the speed of construction. They mastered a material science of openness and collaboration, prioritizing longevity through integration. One philosophy sees the environment as an adversary to be sealed out. The other sees it as a partner in an enduring chemical dance. The staggering scale of our modern construction comes with a hidden atmospheric cost. Every ton of Portland cement we produce releases nearly a ton of carbon dioxide into the air, a direct result of the fossil fuels burned to reach the extreme temperatures needed to calcine limestone. In total, this single industry is responsible for roughly 8% of all global carbon emissions every year, a figure that underscores the profound environmental weight of our built world. This is the urgent, modern crisis against which the Roman formula now stands in stark contrast. Their concrete required significantly less lime, and the lime they did use was produced in simpler kilns at far lower temperatures. More importantly, the volcanic ash that formed the bulk of their mix required no energy-intensive processing at all. It was simply harvested from the earth. But the sustainability advantage goes far beyond the initial production. Think of a modern bridge or seawall with a projected lifespan of 50 years. Over the course of a single millennium, that structure would need to be completely torn down and rebuilt at least 20 times, with each cycle incurring anew the carbon cost of manufacturing, transportation, and construction. A Roman harbor built once serves for 2,000 years. Its durability translates into a radical reduction in lifetime carbon emissions, eliminating the repeated cycles of demolition, waste, and fresh production. This presents us with a powerful and reflective question. Is our pursuit of rapid, cheap construction actually the more expensive path in the long run, when we account for the cumulative environmental toll? Reviving the principles of this ancient technology is not merely an exercise in historical curiosity. It is emerging as a serious blueprint for a greener, more resilient future. Researchers are now actively exploring how to create modern versions of Roman concrete, using industrial byproducts like fly ash from coal plants or slag from steel production as contemporary pozzolans. These materials, often considered waste, could be transformed into the backbone of a new, low-carbon construction paradigm. The goal is not to copy the Roman recipe exactly, but to rediscover its core philosophy, a philosophy of material patience and environmental synergy. This approach could allow us to build infrastructure that heals its own cracks, resists corrosive elements, and stands for centuries, not decades. It shifts the priority from the speed of construction to the longevity of service, from a model of constant consumption to one of enduring stewardship. The potential is immense, offering a path to drastically reduce the carbon footprint of our cities and coastlines. Yet, a significant hurdle remains, one of practicality and scale. Can a material designed for the slow, deliberate pace of an ancient empire be adapted to meet the frenetic demands of the 21st century? But can an ancient wisdom be translated into a modern formula? In laboratories from Cambridge to Berkeley, scientists are now attempting to do just that, not by slavishly copying the Roman recipe, but by reverse engineering its core principles. The challenge is immense. We are not simply trying to find another volcanic deposit. We are trying to understand the reactive dance between lime, ash, and water at a molecular level, and then recreate that dance using the materials of our own time. Leading this charge are teams at institutions like the Massachusetts Institute of Technology and the University of California, Berkeley. Their work moves beyond mere analysis of ancient samples into the active realm of creation. They are experimenting with modern pozzolans, industrial byproducts like fly ash from coal plants or slag from steel mills. These materials, often seen as waste, share a key characteristic with the ash from Pozzolana, a high content of reactive silica and alumina. When combined with lime under the right conditions, they can undergo similar long-term pozzolanic reactions, but the real breakthrough attempt lies in replicating the hot mixing process. Researchers are carefully engineering modern versions of those ultra-reactive lime clasts, creating what they call a ductile concrete. The goal is to intentionally seed the mix with these nanoscale reservoirs of potential, designing a material that is born with a self-healing capability. This is the critical leap, from observing a 2,000-year-old artifact to programming that same resilience into a material mixed next week. It is the translation of an empirical art, perfected through generations of trial and error, into a reproducible 21st century science. The potential applications are transformative. Imagine bridges that seal their own stress cracks before corrosion can start, or underground pipelines that mineralize small leaks, or coastal barriers that grow more resilient with each passing storm. This new class of concrete would not just be stronger, it would be smarter, designed with a kind of material memory that anticipates its own weaknesses. Yet for all this promise, significant obstacles stand in the way of turning lab samples into the foundations of our cities. The first is the tyranny of time itself. How do you test a material designed to improve over centuries? Accelerated aging tests in labs can simulate decades of wear in months, but they cannot truly replicate the slow, complex chemical conversations that happen over millennia. Convincing engineers and construction firms to adopt a new material requires proven long-term data, the very data that, by definition, we cannot yet have for a modern replica. Then there is the challenge of standardization and scale. The Roman formula thrived on local variation, using whatever reactive ash was available nearby. Our modern construction industry, however, is built on global supply chains and strict, uniform codes. A concrete mix must perform identically whether it is poured in Boston or Bangkok. Creating a reliable, consistent version of this ancient, variable technology is a monumental engineering puzzle. Finally, there is the simple inertia of the existing system. The entire world's infrastructure is built around Portland cement. Factories, supply networks, engineering curricula, and building codes are all optimized for it. Introducing a new paradigm requires not just a better product, but a retooling of an entire industrial ecosystem. The cost of change, both financial and institutional, is a formidable barrier. So we are left with a tantalizing dilemma. We hold in our hands the chemical blueprint for a material that could last 1,000 years, yet we are constrained by the economic and temporal rhythms of a world that thinks in decades. This gap between ancient possibility and modern practicality is where the next chapter of this story will be written, a chapter that forces us to ask a deeper question about what we value. Is our ultimate goal to build quickly or to build forever? The answer may depend on rediscovering a patience we have long forgotten. A Roman harbor could take years to reach its full strength, a timeline of patience written in stone. Our world operates on a different clock. The financial models behind modern construction demand rapid returns, where a bridge or building must be operational in months, not years. Investors fund projects with strict completion schedules, and delays cascade into massive financial penalties. A material that requires seasons to cure is, in today's economic language, simply too expensive to wait for. This is the first and perhaps most fundamental hurdle, a direct conflict between the chemistry of longevity and the economics of immediacy. Even if we perfect the recipe, who will pay for the time it needs to become truly immortal? The problem extends beyond the calendar and into the very ground beneath us. The Roman Empire was built on a lucky geological accident, the abundant volcanic deposits around the Bay of Naples. Their reactive ash was a local secret with global reach, shipped via imperial supply lines we no longer possess. To replicate this today on a planetary scale, we would need to locate, certify, and establish entirely new global supply chains for specific reactive natural pozzolans. Our modern industry thrives on standardization and interchangeable parts, not on sourcing unique minerals from specific volcanoes. This lack of a ready-made, reliable material pipeline is a massive logistical barrier. Yet, the greatest obstacle may be invisible, embedded in the rulebooks that govern every structure around us. Our entire system of building codes and engineering standards has been meticulously developed over a century around the known, predictable behavior of Portland cement. Engineers can calculate to a precise degree how a steel-reinforced concrete beam will behave under load after 28 days or 50 years. This predictability is the bedrock of safety and insurance. Introducing a new material with a different, slower curing profile and a long-term reactive chemistry is like speaking a foreign language to this entire regulatory body. It would require decades of independent testing, costly certification processes, and a fundamental rewrite of the guidelines that every architect and engineer relies upon. The construction industry is inherently conservative, and for good reason. Lives depend on its reliability. Adopting a new paradigm requires not just a better product, but a leap of faith across a canyon of established practice. This creates a powerful inertia, a preference for the familiar devil we know over the ancient angel we are still learning to understand. We are caught in a classic, frustrating tension. The long-term benefit for our planet and our descendants is incalculable, a vision of infrastructure that lasts for millennia with a fraction of the carbon footprint. But the short-term costs, the retooling of global industry, the retraining of professionals, and the reworking of financial models are dauntingly real and immediate. This tension forces an uncomfortable but necessary question. How did the Romans, without our laboratories or global standards, develop such an advanced material? Their process was not faster, but their priorities were fundamentally different. They were not building for a quarterly report or a political term. They were building for the glory of Rome and for eternity, an investment in a legacy that would outlast empires. Their material science was an extension of that worldview, a patient collaboration with nature that accepted time as a partner, not an enemy. Our challenge is not merely to rediscover their formula, but to rediscover a sliver of that patience within the relentless momentum of our own age. The Roman mastery of concrete was not a happy accident of geology. It was the product of a distinct engineering philosophy, one built on relentless, hands-on experimentation. They did not have laboratories, but they had something arguably more powerful, the entire Mediterranean basin as their testing ground. Over centuries, they built harbors in different waters, aqueducts across varied terrains, and monuments under diverse skies, each project a massive, long-term experiment. When a seawall in Caesarea stood firm after a century of storms, that data was not logged in a spreadsheet. It was absorbed into the collective wisdom of the building guilds and passed down. This was empirical science on a generational scale, a slow, meticulous process of observing what worked in the real world and refining the recipe for the next project. The Roman engineer was first and foremost a keen observer of nature. They developed an intimate, localized knowledge of materials geology, understanding that the best sand for concrete in Naples might differ from the ideal mix in North Africa. The architect Vitruvius, in his 10-volume work on architecture, dedicated entire chapters to the sourcing of materials. He wrote of the necessity to choose the right sand, to test its quality by rubbing it between the hands, and to select lime from stone that was white and pure. He emphasized that materials must be suited to their purpose and their place, a principle of context-sensitive design we often override today in favor of universal standards. The philosopher Seneca also reflected on this practical wisdom, noting that we discover the laws of nature not just by thought but by use. For the Romans, knowledge was not abstract, it was embedded in the act of building itself. Their process was one of iterative observation and adaptation. A recipe was not a fixed formula, but a living guideline adjusted for local stone, local water, and local climate. This slow accumulation of practical, place-based knowledge formed the true backbone of their architectural legacy. It was a mindset of patient optimization, where success was measured not in quarterly returns, but in the silent endurance of a structure over generations. This cultural engine of experimentation is what allowed them to stumble upon and then refine the chemical miracle of their concrete. When the empire fell and this continuous chain of observation was broken, the deep why behind their recipes faded, leaving behind only the mysterious, enduring what. The loss of this iterative, empirical mindset is perhaps as profound as the loss of the chemical formula itself. It invites us to look at their remaining structures not as finished artifacts, but as frozen chapters in a centuries-long dialogue between builder and material. What other lessons in resilience, in passive design, or in environmental harmony are still encoded in their stones, waiting for us to learn the language of their patience? The genius of Roman concrete was not confined to celebrated ports or soaring domes. It was the quiet, unseen foundation of an empire's daily life, a material so trusted it was buried underground and submerged in darkness. Beneath the iconic arena of the Colosseum in Rome lies a hidden labyrinth of tunnels and chambers, a backstage world for gladiators and animals. These foundations, constantly damp and under immense load, are not made of traditional cut stone but of concrete. Mixed with local tuff and brick rubble, this formulation prioritized stability and resistance to moisture, proving the material's versatility for massive, earth-bound structures. Far to the east, in the city that would become Constantinople, engineers faced a different challenge, securing a reliable water supply against siege. Their solution was the vast subterranean basilica cistern, supported by a forest of 336 marble columns. But the true marvel lies beneath the floor, where a thick, waterproof concrete lining, likely using a local pozzolanic ash from the Aegean, created an artificial cavern that held millions of gallons of water for centuries without leaking. This was concrete as a sealant, engineered for perpetual dampness. Meanwhile, across the rural landscapes from Gaul to North Africa, the humble aqueducts that carried water to distant cities showcase yet another adaptation. Their channels, often lined with a special hydraulic concrete called opus signinum, mixed crushed pottery and tile with lime to create an ultra-smooth, waterproof finish that minimized friction and resisted mineral buildup. Each of these applications, from foundation to reservoir to conduit, demanded a slightly different balance of ingredients, a tweak in the formula for local sands, available aggregates, and specific environmental stresses. This was not a single, rigid recipe copied from a scroll. It was a living, adaptive technology, a broad principle of reactive chemistry applied with local intelligence. The geographic spread of these enduring structures is the ultimate proof of concept. It tells us the core wisdom was portable and robust, not dependent on one perfect volcanic hill in Italy, but on an understanding of how to create chemical resilience with whatever reactive materials a region offered. For modern researchers, this diversity is a treasure trove of new clues. By comparing the concrete from a dry aqueduct in Spain to that of a waterlogged cistern in Turkey, scientists can map how the Romans fine-tuned their pozzolanic reactions for different threats, be it constant hydration, heavy compression, or flowing water. This ancient recipe book, written in stone across 3 continents, offers us more than one formula to rediscover. It provides a masterclass in adaptive material science, showing how a deep principle can flex to meet the needs of the real world. To understand their material genius, we must step into the Roman mind. They did not speak of calcium silicate hydrates or pozzolanic reactions. Their language was one of elements and transformation, a worldview shaped by the practical alchemy of the builder's yard. At its heart was a profound respect for the transformative power of fire, water, and earth. Fire turned solid limestone into a caustic, reactive powder, a process called calcination that felt like a liberation of spirit from stone. Water, when poured onto this quicklime, created a violent, steaming rebirth, slaking it into a malleable paste. And earth, specifically the volcanic ash from Pozzolana, was no inert dirt. It was a sacred, reactive dust that completed the marriage. This elemental dance was their functional chemistry. It produced results so consistent and extraordinary that it formed the physical backbone of an empire, all without a single textbook on molecular bonds. The closest they came to a manual was the encyclopedic work of Pliny the Elder. In his sprawling natural history, he devoted entire books to the sources of stone, the making of lime, and the properties of different sands. He wrote not as a theoretical chemist, but as a meticulous observer, documenting which pit produced the best lime for stucco, and which volcanic ash made the hardest cement for harbor works. His work captures a different way of knowing, one rooted in sensory experience, trial across generations, and a holistic view of materials as partners in a great transformation. This empirical, hands-on wisdom was their laboratory. A master builder knew the feel of good pozzolana between his fingers, the sound of lime slaking properly, and the look of a mix that would set true. This knowledge was passed not through equations, but through apprenticeship and the shared memory of what worked on 100 different sites. Bridging this ancient, experiential know-how with the precise language of modern chemistry is our grand challenge today. We have the tools to see the atomic structures they created, but we must also learn to appreciate the intuitive, holistic process that led them there. It is the difference between reading the sheet music and understanding the feeling of the symphony. Their success forces us to ask, what other profound truths about our world have we overlooked because they were written in the language of experience rather than the dialect of the lab? Roman concrete stands not as a lonely marvel, but as a brilliant star in a much larger constellation. Across the ancient world, from the jungles of Mesoamerica to the river valleys of China, builders discovered a shared secret. Durability emerges from partnership, not domination. They looked to their own landscapes and found organic binders that could turn simple earth and stone into something timeless. In China, during the Ming Dynasty, engineers faced the monumental task of fortifying the Great Wall. Their solution was not just stronger mortar, but a culinary innovation. They began mixing a paste of sticky rice, a staple of their diet, into their standard lime mortar. This was not mere folklore. Modern analysis reveals the amylopectin in the rice acted as an organic inhibitor, controlling the growth of calcium carbonate crystals. The result was a mortar that was more compact, more resistant to water, and far more durable than plain lime. The Great Wall's resilience is in part a testament to a recipe that blended the pantry with the quarry. Meanwhile, halfway across the globe, the Maya of Central America were mastering a different kind of organic chemistry. To stucco their towering pyramids and ornate palaces, they used a lime plaster, but they fortified it with the sap from local trees, particularly the bark of the chucum tree. This natural polymer created a flexible, waterproof coating that could withstand the region's torrential rains and humid climate. Their structures became living extensions of the forest, protected by its own resins. These parallel discoveries reveal a profound pattern. Civilizations separated by vast oceans and with no possible contact each arrived at the same fundamental insight. The most powerful building materials often come from integrating processed natural products with mineral bases. They did not have a global supply chain for Portland cement. They had a deep, localized knowledge of their environment. They asked not what universal powder could be imported, but what sticky, resilient, or reactive substance their own land provided. This is a global human tradition of material science, one where innovation was driven by necessity and a keen observation of local resources. The Roman use of volcanic ash fits perfectly within this tapestry, a pinnacle of this same empirical, place-based logic. Each civilization's solution was unique to its ecology, yet all pursued the same goal, creating a synthetic stone that was more than the sum of its parts, a material that borrowed strategies from the biological world. This collective wisdom points to universal principles of durability that our modern industry, in its quest for uniform, predictable commodities, has largely sidelined. We chose a path of standardization that often ignores local context. What if, instead of forcing one material to fit every environment on Earth, we revived this ancient, distributed intelligence? The potential is staggering. Imagine a world where buildings in coastal regions incorporate seawater reactive minerals inspired by Roman harbors, where structures in seismic zones use flexible, natural polymer composites learned from Maya plasters, and where regions with specific agricultural byproducts like rice hull ash or sugarcane bagasse use those waste streams to create stronger, carbon-sequestering concrete. Learning from this global tapestry is not about nostalgia. It is about accelerating modern discovery. By studying these ancient successes not as isolated curiosities, but as a diverse dataset of proven biomineral composites, we can shortcut centuries of trial and error. We can ask new yet ancient questions. What locally abundant, renewable resource in this valley, on this coast, could become the key to a more resilient architecture here? The answers are likely already growing in the fields, lying in the soil, or flowing in the rivers, waiting for us to look with the same integrative eyes as the builders who came before. The loss of their concrete recipe was never a simple case of misplaced instructions. A technology this advanced does not vanish in a library fire. It dissolves with the civilization that nurtured it. The Roman Empire was not just a political entity. It was an unparalleled administrative machine. It maintained imperial standards, state-run quarries, and a professional corps of military engineers who carried proven techniques from Britain to Syria. This vast network ensured that the specific volcanic ash from Pozzolana could be shipped to a harbor construction site in Judea, and that the master builder there knew the exact hot mixing technique perfected over generations. The knowledge was systemic, embedded in the logistics and institutions of the state itself. When that centralized state began to fracture, the first thing to go was not the knowledge in a single person's mind, but the quality control across a continent. Specialized engineering knowledge, once a portable imperial asset, retreated into isolated local guilds. A builder in a crumbling province might still know how to make a decent mortar, but he no longer had access to the ideal ash or the broader understanding of why it worked. The knowledge became localized, then simplified, and over generations it fragmented into folklore. As the empire's borders contracted under pressure, societal priorities underwent a brutal shift. The grand, long-term vision required for aqueducts and harbors projects that pay off over centuries was a luxury that fading administrations could no longer afford. Immediate concerns of defense and survival took absolute precedence. The economic engine that funded these monumental civic works, a complex system of taxation, trade, and slave labor seized and broke down. The very concept of investing in infrastructure meant for grandchildren became unimaginable in a world focused on the next harvest or the next raid. This reveals a profound truth we often overlook. A technology is not merely a formula scribbled on parchment. It is a living process deeply rooted in a supportive ecosystem, a specific economy that can fund it, a political structure that can organize it, and a cultural mindset that values its long-term payoff. The concrete did not fail the Romans, their entire world. The intricate system that created and sustained the concrete gradually fell apart around it. The recipe was a seed that could only grow in a particular kind of soil. When that soil eroded, the seed, though potent, became inert. This is why simply finding the chemical formula in a modern lab is only half the battle. Its recovery requires more than mixing the right minerals. It asks us to rebuild something of the supportive context, to reignite a societal patience for projects whose full strength reveals itself over lifetimes, not fiscal quarters. The stones that remain are therefore more than ruins. They are fossils of an entire way of thinking about time, community, and our place in the world. Deep within a polished cylinder of ancient concrete, a story unfolds at 1 billion times its normal speed. This is not science fiction, but the reality of modern digital archaeology, where tools like micro-CT scanners act as non-destructive time machines. Unlike traditional methods that required crushing a sample to dust, these advanced scanners use X-rays to create a perfect three-dimensional map of the material's internal universe, preserving every pore, every crack, and every one of those mysterious lime clasts in pristine digital form. Scientists can now navigate through this captured landscape virtually, tracing the intricate pathways where seawater filtered in and new minerals crystallized, observing the material's history as a dynamic, three-dimensional fossil. This allows researchers to ask new kinds of questions. How did the crack network evolve over the 1st century versus the 10th? How are the lime clasts distributed, and what is their precise relationship to the healed fissures around them? The static slice under a microscope has given way to an immersive, navigable timeline of resilience. The investigation goes even deeper at facilities like synchrotron light sources. Here, beams of intense X-rays, millions of times brighter than the sun, are focused onto a microscopic spot within the sample. Through a technique called X-ray diffraction, these beams don't just show structure, they reveal identity. They can pinpoint the exact crystal phases present, distinguishing between the original compounds and the new minerals that formed centuries later. This is how scientists confirmed the ongoing growth of tobermorite and philipsite within 2,000-year-old harbor concrete. The synchrotron acts as a chemical historian, reading the mineralogical ledger written atom by atom over millennia. It can show the gradient of change from the concrete's sun-baked surface to its damp, sheltered core, mapping the chemical conversation between the material and its environment in exquisite detail. This data is so vast and complex that human analysis alone is insufficient. This is where artificial intelligence enters the laboratory. Machine learning algorithms are trained to recognize patterns in these enormous datasets, to spot correlations between a specific mix design, the nanoscale architecture it produced, and the long-term performance observed in the real world. The AI can process millions of data points from scans of samples from different sites and eras, searching for the common threads that define success. It is a powerful new partner in decoding an ancient empirical art, helping to translate the Romans' tactile, experience-based knowledge into a reproducible, quantitative language for the modern age. Together, these tools represent a fundamental shift from analyzing a material state to simulating its life cycle. Researchers are no longer just cataloging what is there, they are beginning to model how it got there and where it is going. By feeding the high-resolution scan data into computational models, they can create digital twins of Roman concrete samples. These virtual specimens can then be subjected to simulated centuries of seawater exposure, freeze-thaw cycles, or seismic stress, all within a supercomputer. The goal is to watch the self-healing mechanism in action, to see, in accelerated simulation, how a crack propagates, intersects a lime clast, and triggers the recrystallization that seals the breach. This moves the quest from reverse engineering a snapshot to understanding the entire movie, from the hot mix of the first day to the silent repair of the 1000th year. This digital frontier offers our greatest hope for a complete recovery of the lost wisdom. It provides a bridge between the monumental scale of Roman construction and the nanoscale chemistry that made it possible, and between the slow patience of ancient builders and the urgent need for sustainable solutions today. The promise is a new generation of materials designed not just for strength, but for an active, intelligent longevity, materials with a built-in memory of how to endure. Yet, even with these dazzling digital time machines, one profound human element remains elusive: the mindset that valued such patience in the first place. A cornerstone of the Pantheon bears a simple, telling inscription. It was built by Marcus Agrippa, son of Lucius. This was not a signature for his own time, it was a claim laid down for eternity. The Roman builder worked with a temporal horizon that stretched across generations, a mindset where a structure's true value was measured not by its completion date, but by its endurance. Their concrete is the physical crystallization of this philosophy, a material science dedicated to permanence. It was an investment in a future they would never see, a gift to an unborn citizenry. This stands in stark relief against the economic logic that governs much of our modern built environment. We operate on asset life cycles, depreciation schedules, and cost-benefit analyses that often cap a bridge's expected service at 50 years. We have even institutionalized a form of planned obsolescence, not necessarily through malicious intent, but through a system that prioritizes lower initial cost and faster returns over ultimate longevity. The material choice follows the financial logic. Why specify a concrete that takes years to reach peak strength and costs more upfront, when a cheaper, faster-setting mix meets the code requirements for the project's designated lifespan? This creates a self-fulfilling prophecy of transience. We build for a calculated expiration date, and our materials, obedient to that vision, oblige. The Roman harbor at Caesarea had no such expiration date stamped on its plans. Its builders were not catering to a quarterly report or a political term. They were competing with the sea itself and with time. This divergence raises a quiet but profound question about legacy. Are we, in our relentless pursuit of speed and immediate efficiency, inadvertently constructing a more brittle world, one where the constant churn of demolition and reconstruction becomes a permanent, resource-hungry cycle, and where little is built to outlast the people who built it? The contrast in the concrete itself becomes a powerful metaphor for these competing temporal values. One material is closed, finished, and destined to degrade. The other is open, reactive, and designed to evolve. One sees time as an enemy to be outrun, the other sees time as a partner in a slow, strengthening dance. This is not merely a technical difference, it is a philosophical one, asking us what we value more, the convenience of the present or the resilience of the future. The silent, enduring stones of the ancient world challenge us to reconsider the weight we give to each. Its dome is a perfect hemisphere of unreinforced concrete, a form of breathtaking geometric purity that has defied gravity for almost 19 centuries. To stand beneath the Pantheon's oculus is to experience a paradox of weight and light, a feeling of impossible lightness carved from a material we associate with mass and burden. This is not just a roof, it is a structural enigma, a feat of engineering so advanced that it would not be surpassed in span until the dawn of the modern steel age. For over 1,700 years, it held the title as the world's largest dome of its kind, a silent reign of architectural supremacy. Its survival is a masterclass in Roman empirical genius, written not in equations, but in the deliberate, layered composition of the concrete itself. The builders understood a fundamental principle: the crushing weight of the dome increased exponentially toward its base. To manage this immense load, they employed a brilliant strategy of material grading. They did not use a single, uniform concrete mix from foundation to peak. Instead, the recipe changed strategically with height. The heavy, foundational layers near the ground were mixed with dense, robust aggregates like travertine and brick rubble, providing a solid, stable base. But as the walls curved inward to form the dome, the mix transformed. In the upper reaches, the builders incorporated progressively lighter materials. They used porous volcanic stones like tuff, and for the very top of the dome surrounding the oculus, they used pumice, a frothy, air-filled volcanic glass so light it can float on water. This was not a random choice, it was a calculated act of structural optimization. By lightening the load at the summit, they dramatically reduced the outward thrust and tensile stress on the lower walls, allowing the entire structure to behave more like a monolithic shell. This sophisticated understanding of material grading reveals a physics intuition that feels remarkably modern. They were essentially creating an ancient form of lightweight composite, tailoring the material's density to match the precise structural demands at every point. The dome's formulation was likely distinct from the maritime concrete used in harbors. While the harbor mix was designed for a slow, watery chemical conversation with the sea, the Pantheon's concrete was engineered for dry, compressive strength and, critically, a degree of flexibility. This brings us to its most astonishing performance record, its survival through the seismic turmoil of the Italian peninsula. Rome has experienced numerous earthquakes over the millennia, events that have toppled countless later structures. Pantheon's dome has swayed and settled, but it has never shattered. This points to a property modern engineers call ductility, the ability of a material to deform slightly under stress without fracturing. The Roman concrete, with its complex binder of lime and pozzolana and its graded aggregate, appears to have possessed a natural resilience, a capacity to absorb and redistribute energy through micro-cracking and internal adjustments. It was not a brittle ceramic but a tough, stone-like composite. The giant crack that is visible in the dome's interior lining is not a sign of failure, but a testament to this very process, a fossilized record of a moment of intense stress that the material accommodated and survived. The Pantheon, therefore, is far more than a beautiful relic. It is a full-scale laboratory experiment that has been running for nearly 2,000 years, demonstrating the success of a holistic design philosophy where material science and structural form were in perfect dialogue. Every choice, from the mix in the mortar to the shape of the void, was an integrated part of a single, enduring vision. It stands as the ultimate case study, proving that their lost formula was not a single trick, but a versatile and profound system of thought, one capable of creating both a fortress against the sea and a whisper of stone against the sky. The principles that built an empire on Earth may one day anchor our first permanent homes on other worlds. This is not science fiction, but a logical extension of the Roman philosophy of in situ resource utilization, a term modern space agencies use for the vital strategy of using local materials. The Romans did not ship sacks of Pozzolana ash to every corner of the Mediterranean out of stubbornness. They did it because it was the only practical way to build at scale. On the Moon or Mars, shipping bags of Portland cement from Earth is astronomically and literally cost-prohibitive. Every kilogram lifted from Earth's gravity well is a fortune spent. The solution, then, mirrors the ancient one. We must learn to build with the dust beneath our boots. lunar regolith, the fine, abrasive soil that covers the moon, and Martian soil are not inert dirt. They are the products of ancient volcanic activity and cosmic bombardment, rich in silicates and minerals. To a materials scientist, they look remarkably like potential pozzolans. The dream is to take this local dust, combine it with a binder that could be produced from processed local minerals or even transported in a concentrated form, and initiate a slow, durable chemical set, creating a true extraterrestrial concrete. The advantages go far beyond simple resource savings. The environments on the Moon and Mars are brutally hostile, with temperature swings of hundreds of degrees, constant bombardment by micrometeorites the size of dust grains, and in the case of Mars, potential chemical reactions with perchlorates in the soil. A modern Portland cement structure would be brittle, vulnerable to the relentless cycle of expansion and contraction, and would slowly fracture under this assault. A material engineered with Roman-inspired principles, however, could offer a revolutionary advantage: self-healing. Imagine a habitat wall molded from processed lunar soil that possesses a network of latent lime-like compounds. When a microcrack forms from a tiny impact or thermal stress, and the near vacuum or thin Martian atmosphere allows moisture from within the habitat to seep into the fissure, it could trigger a recrystallization event. The crack seals itself, maintaining structural integrity and air pressure safety without any need for an astronaut to perform a risky external repair. This transforms the material from a passive shield into an active participant in its own preservation. The ancient Roman quest for a material that collaborated with its environment finds its ultimate test in an environment that wants to erase all traces of us. This speculative vision connects the deepest past to the farthest future, suggesting that the lost wisdom of Roman concrete is not a relic but a timeless toolkit for resilience. It asks us to see their harbors and domes not as endpoints, but as prototypes for a philosophy of building that could one day shelter human life under an alien sky. The journey to recover their secrets, therefore, becomes more than historical curiosity. It becomes a form of preparation, a way of packing for a very long trip by looking back at the foundations we have already and so enduringly laid. Yet for all its legendary endurance, Roman concrete was never a magical, unbreakable stone. It is vital to separate the verified chemistry from the persistent myths that have grown around it. One common misconception is that these ancient structures are universally indestructible. This is simply not true. We have countless ruins after all. Roman concrete degrades under specific, aggressive conditions, particularly when exposed to acidic rainwater or pollution, which can slowly dissolve its lime binder. Its legendary strength is not an absolute shield, but a highly specialized resistance, one perfectly tuned for the alkaline, mineral-rich environment of seawater. In a marine setting, it thrives. In a modern acid rain shower, it can suffer. This nuance is crucial. It means the material was not invincible, but brilliantly adapted. Another layer of myth suggests the recipe contained bizarre, alchemical ingredients, like animal blood, milk, or even eggs. While ancient texts sometimes mention such additives for mortars or plasters, there is little to no archaeological evidence that they were used in structural concrete on a scale that would explain its durability. These stories likely grew from later attempts to explain a lost technology or from the symbolic power of such substances in ritual. The real magic was far more mundane and far more profound in the volcanic ash and the hot mixing process. Perhaps the most important clarification is that there was no single, secret formula locked in an emperor's vault. The superiority of Roman concrete was not a monolithic secret, but a flexible system. It was a combination of a core chemical principle, the pozzolanic reaction, applied with intelligent design like the graded aggregates in the Pantheon dome, and a favorable, long-term interaction with specific environments. This is not a diminishment of their achievement, but its elevation. It transforms the story from one of a lost password to a recovered philosophy, a way of thinking about materials that collaborates with the world rather than resisting it. Grounding this discussion in verified science does not strip away the wonder. It redirects our awe to the right place, not to mythical potions, but to observable, replicable chemical conversations that we are only now beginning to fully decode. This clarity strengthens the entire endeavor, ensuring that the quest to revive this ancient wisdom remains a credible chapter in material science, not a slide into speculative legend. The word itself carries the ghost of their philosophy. Our term concrete comes directly from the Latin concretus, meaning grown together, condensed, or hardened. It is a perfect linguistic fossil, capturing the essence of the material not as a dead assembly, but as an active process of unification. This was no accidental naming. It reflected a worldview where disparate elements, lime and ash, water and stone, were brought into a new, inseparable whole. This concept of things growing together into a solid mass seeped from the building yard into the very fabric of Roman thought, eventually giving us not just a building material, but an adjective for anything tangible, real, and unified. The language preserves the memory of their integrative genius, a quiet echo in our daily speech that we seldom pause to hear. But the legacy extends far beyond vocabulary. It is stamped into the principles of law and civic duty that underpin Western society. The Romans were meticulous bureaucrats, and their approach to public construction was governed by formal codes and standards. Figures like the architect Vitruvius did not merely write about proportions. He detailed specifications for materials and methods, establishing early notions of professional liability. A builder or an engineer who took public contracts for an aqueduct or a basilica was held to a standard of care, and shoddy work that led to collapse could result in severe penalties, including financial ruin. This was not merely about punishment, it was about ensuring the safety and permanence of public trust, literally built into the city. The concept that a constructor bears responsibility for the long-term integrity of their work, a cornerstone of modern construction law and professional engineering ethics, finds a clear precedent in these ancient regulations. The Roman focus on durable public works, from roads to sewers to harbors, also reinforced a powerful idea of civic responsibility. The state, through its engineers and its treasury, had a duty to provide enduring infrastructure for its citizens. This investment in the public good, in projects meant to outlast any single administration, helped shape a legal and cultural expectation that governance is linked to tangible, lasting provision. When we today debate infrastructure bills or hold municipalities accountable for bridge safety, we are participating in a conversation about civic responsibility that the Romans, through their stone and mortar, helped to codify. So the story of Roman concrete is not confined to ruins or chemistry labs. It is woven into the intangible architecture of our civilization, into the words we use to describe reality, and the legal frameworks we build to ensure collective safety. The material shaped minds as much as monuments, teaching generations that building for the future requires more than good intentions. It requires codes, accountability, and a profound patience woven into both law and language. This cultural dimension completes the picture, showing us that a truly transformative technology never just stands there. It becomes a foundation for how a society thinks, governs, and endures. The true search for this lost formula does not happen in a single laboratory. It unfolds in a space between disciplines where the precise language of chemistry meets the interpretive art of history. A materials scientist can identify a crystal of tobermorite under an electron microscope, but she cannot tell you why the Roman builder at Ostia chose one volcanic sand over another. For that, she needs the historian, someone who can pore over the weathered pages of Vitruvius's De Architectura, not just as an ancient text, but as a coded recipe book. When Vitruvius writes about selecting white, pure lime or testing sand by rubbing it between the hands, he is not offering poetry, he is providing a quality control checklist from 2,000 years ago. The historian translates this empirical wisdom, this tactile knowledge, into a context the modern researcher can use, yet a text alone is not enough. Its instructions must be grounded in physical evidence. This is where the archaeologist enters the collaboration with a trowel and immense care. Their role is to extract a pristine sample of concrete from a ruin, not from a collapsed wall exposed to modern pollution, but from a protected core, a fragment that has been sealed from the elements for centuries. This sample is a time capsule, and its chemical story depends on it being uncontaminated. One stray molecule from a modern handsaw can skew the data, sending chemists down a false path. Once secured, the sample's journey continues to the geologist. Pozzolana is not a single substance, it is a category. The specific ash from Pozzolana has a unique mineral fingerprint, different from the volcanic deposits in the Aegean or North Africa. A geologist can analyze the sample's aggregate, tracing its elemental signature back to a specific region, even a specific hill. This tells the collaborative team not just what the Romans used, but where they sourced it for a given project, revealing trade routes and local adaptation strategies. Finally, the material scientist takes this contextually rich sample and peers into its nanoscale universe. With the historian's text as a guide, the archaeologist's sample as the true artifact, and the geologist's sourcing as a map, the chemist can now ask sharper, more meaningful questions. Instead of just asking what minerals are present, they can ask why they are present in this specific configuration from this specific site. This interdisciplinary synthesis is the real engine of discovery. It turns a chemical analysis into a chapter of human history. The lost formula is not being found in a single field's journal, it is being assembled in the conversation between them. This collaborative model is a powerful blueprint for solving other grand historical puzzles, from the steel of Damascus swords to the concrete of the Roman world. It proves that the deepest mysteries are often locked in a vault with many keys, and no single discipline holds them all. This pursuit is far more than a technical puzzle. It is an urgent ethical question written in the rising tides. Our coastlines are home to hundreds of millions of people, and the infrastructure meant to protect them, our seawalls, levees, and breakwaters, is often engineered with a lifespan measured in decades. We are, in essence, handing the next generation a shield we know will crack, asking them to bear the cost and danger of rebuilding what we chose not to build well. This is not merely an engineering challenge, it is a profound matter of intergenerational justice. When we opt for cheaper, faster materials that degrade on a human timescale, we externalize the true cost onto our children and grandchildren. We force them to pay, both financially and in terms of safety, for our preference for immediate economy. The Roman philosophy of durability inverts this equation. It embodies a principle of stewardship, where the builder accepts a greater burden upfront so that future communities inherit not a liability, but an asset that has grown stronger. In an era defined by climate change and increasingly severe weather, this long-term thinking transforms from a luxury to a survival strategy. Resilient infrastructure is the bedrock of community safety, the difference between a storm surge being managed and a neighborhood being erased. Investing in materials that can endure for centuries, rather than just a few decades, is a direct investment in human security. It reduces the constant cycle of demolition and reconstruction, which itself consumes vast resources and energy, creating a spiral of waste. More importantly, it creates stable, protected spaces where communities can plan for the long term, rather than perpetually recovering from the last disaster. The Romans built for eternity to glorify their empire, but the unintended legacy of that ambition is a potential blueprint for modern resilience. their concrete offers a powerful metaphor for a different kind of relationship with the future, one based on care and foresight rather than deferral and risk. Recovering this knowledge, then, shifts from a fascinating historical recovery mission to a moral imperative for sustainable stewardship. It asks us to look at the silent, enduring harbor not as a relic but as a question. What kind of ancestors do we intend to be? Will we be remembered for the clever speed of our construction, or for the enduring safety of what we chose to leave behind? The sunken harbors of antiquity and the humming laboratories of today are connected by a single, profound question. This is not merely a search for a forgotten recipe, but a journey that quietly reshapes our understanding of progress itself. For generations, we measured advancement by speed and novelty, by what we could build bigger and faster than ever before. The silent endurance of Roman concrete asks us to consider a different metric: the wisdom of longevity. It reveals that our most modern material science, for all its precision, abandoned a fundamental insight that true resilience comes from collaboration, not control. The Romans did not see seawater as a corrosive enemy to be sealed out. They welcomed it as a chemical partner in a strengthening dance that would last millennia. Their concrete was never a finished product. It was an initiated process, a material with a kind of embedded patience, seeded with microscopic repair kits and designed to converse with the world around it. This ancient approach challenges the very core of our industrial philosophy, which often prioritizes immediate efficiency and uniform predictability over environmental synergy and long-term adaptation. In our race forward, we left behind a blueprint for building things that think in centuries, a language of endurance we are only now relearning. As we face a future of rising seas and strained resources, this recovered knowledge shifts from historical curiosity to a vital tool. It offers more than a stronger mix for our seawalls. It provides a new lens through which to view our entire built environment. What if our bridges could heal their own stress fractures? What if our cities were designed not just to withstand the climate, but to engage with it in a strengthening dialogue? The quest for this lost formula ultimately becomes a mirror, reflecting our own values back at us. It asks whether we are building for the convenience of the present or for the safety of generations we will never meet. The answers we need may not always lie in the next breakthrough, but sometimes in the quiet, enduring lessons of the past, waiting in plain sight to be seen with new eyes. If this fusion of ancient insight and modern possibility resonated with you, consider subscribing for more journeys into history's deepest mysteries. And we would love to hear your thoughts. What other modern challenges do you believe could find their solution in the wisdom of the ancient world?